In the previous video, we've seen how we may use dual simplex to find the new optimal solution after we add a new constraint to the problem. Sometimes the result becomes, the original LP becomes infeasible. Now let's look at the other uses of dual simplex. The second one is that we're going to find the new optimal solution after we change the right-hand side of a linear programming. If you recall what we have learned in week 10, this is called the change tree. If we use the Dakota problem as an example again, we are given the linear programming and then the optimal solution for the original problem. And then now we would like to change the second right-hand side from 20 to becomes 20 plus delta. Suppose we change the second right-hand side to becomes 30, or in other words, delta equals 10. Then the current basis is no longer optimal. The reason is because when we compute the new right-hand side and the new z value, we find out that the new right-hand side has a negative value in x1. So x1 equals 3, and then using what we have learned before, the primal simplex, we cannot proceed further with this table. But now we know that when we have this kind of table, in which for maximization, the row 0 does not have any negative coefficient, but we have a negative right-hand side, it means that we may use dual simplex to solve this problem. So in the dual simplex, we first pick the most negative coefficient. Here it is x1 equals minus 3. And then using that row as the pivot row, we check all the variables that has negative coefficient. Here it is only s2 with negative minus 0.5. So the ratio is the absolute value of 10 divided by minus 0.5, which is equals 20. So now we're going to perform elementary row operation such that the column of S2 becomes a canonical form. So only this position has the coefficient of 1 and all other position has the coefficient of 0. So we perform error and then we obtain this new table. Here we may conclude that since all right-hand sides are non-negative, we have obtained the optimal solution. So this is the optimal solution after we change the right-hand side of the second constraint from 20 to become 30. Finally, the third use of dual simplex is that we may use dual simplex to solve a normal minimization problem. So let's see how we may do this. So given a minimization problem, and then you can see that this problem is normal minimization. First, what we're going to do is we convert the objective to maximization. We do this by multiplying the entire row with minus 1, and then now z becomes z prime. Okay, so now it becomes maximization problem. And then we convert the constraints to standard form, minus E1 for the first constraint, minus E2 for the second constraint. And then we multiply the constraints with minus 1 to make E1 and E2 basic variables. So when we put everything in the table, here's the initial table, we see that we have the correct basic variables, E1, E2, they are both in canonical forms. Now there is one question that I would like to ask at the end of this video. Why can't or don't we do this when we do primal simplex? Remember, when we do the primal simplex, we never do this kind of thing, multiplying the constraint with minus 1 and then E becomes the basic variable. So here's a question that I would like to ask you at the end of this video. But for now, let's proceed with the dual simplex using this initial table. In the first step of dual simplex, we see that we do have negative coefficients. in the right hand side. So we go to the second step. In the second step, we pick the variable with the most negative coefficient as the leaving variable. So E2 is the leaving variable. Then we look at that row and then notice that we have two variables with negative coefficients. So we must perform ratio test for all the variables in this row that has negative coefficients. So for x1, the ratio test is 1 divided by minus 2, take the absolute value, so it is 0.5. And then for x2 is 2 divided by minus 1, take the absolute value, so the ratio is 2. We pick the one with the smallest ratio to becomes the entering variable. So we perform error with the purpose that making this position to have the coefficient of 1, and then all other coefficient they have all other position in that column has the coefficient of 0. So we perform error and then we get this table. Again, in the new table we still have the variable with negative coefficient. A negative coefficient in the right hand side means that we are going to do the step 2 again in the dual simplex algorithm. So the most negative variable becomes the leaving variable. So E1 becomes the leaving variable. And then in this row, we see that we have negative 3 over 2x3 and a negative 1/2 of E2. So we perform ratio test for both variables. So for x3, the ratio test is 1/2 divided by 3 over 2 and take the absolute value, so it becomes 1/3. And then the ratio for E2 is 1/2 divided by minus 1/2, take the absolute value, so the result is 1. We pick the smallest ratio as the entering variable, so x3 becomes the entering variable, and this position becomes the pivot position. So in the next table, x3 must be having the coefficient 1 at that pivot position and 0 in all other positions. Perform error elementary row operations, and then we get the new table that looks like this. So we conclude that because all right-hand side are non-negative, we have obtained the optimal solution. However, remember that we multiply the objective function with -1, so z becomes z prime, and then z prime equals minus 10 over 3, such that the original z is minus of that, minus of minus 0.3. The original z is 10 over 3. So that's how we use the dual simplex to solve normal minimization problem. Now here comes the question. So we are given a normal minimization problem. We convert the constraints into standard form, and then we multiply the constraints with -1 to make E1 and E2 basic variables. Now my question is, why can't or don't we do this in primal simplex? The reason is because if you recall what we did in primal simplex, we need to start with a BFS, basic feasible solution. This kind of solution with E variables equals -4 and -6, they are not feasible in the primal problem because all variables including E1 and E2 in the primal LP must be greater than or equal to 0. So it is not primal feasible, so we cannot proceed with primal simplex. However, because this is dual feasible, we may proceed with dual simplex. So that's the reason. So do not confuse with why we can't do this multiply with -1 before when we learn about simplex. Now why we are able to do this? Well, because before we use primal simplex, we need to start with the BFS, which is feasible in the primal LP. Now we are going to do dual simplex, and then it's okay to have negative right hand side. Even actually the dual simplex require negative right hand side such that it may proceed. So this is two different simplex algorithm, primal simplex and dual simplex, such that what we can't do in primal simplex, we may do that in dual simplex. Okay, so that's the end of the big topic of sensitivity analysis and duality that we started after the midterm exam. And then next week, we are going to move on to a new topic, which is called revised simplex method. So we are still going to talk about simplex algorithm. So see you on the video next week. Thank you.